Welcome to this explainer. We're diving right into the microscopic mechanics that literally build our macroscopic world. We're talking about something fundamental happening every single second all around us, totally invisible to the naked eye, but absolutely crucial to the structure of everything we know. So let's kick things off with a bit of a mystery. Why on earth does it take massive amounts of energy to melt simple table salt? I mean, it's just sitting there in your kitchen shaker, right? Completely unremarkable. But if you actually want to melt it down into a liquid, you've got to crank the heat up to an astonishingly high temperature. To figure out why a common household item like salt is so incredibly stubborn to melt, we really have to zoom all the way down to the atomic level. Here's our roadmap for today's explainer. We're taking a micro to macro journey. We'll hit the quest for atomic stability, making the ionic bond, dot and cross diagrams, the giant lattice structure, and finally, real-world ionic properties. We're starting with single atoms and building all the way up to the physical reality we interact with. Okay, Section 1, the quest for atomic stability and the drive for a full outer shell. Let's meet our microscopic actors whose whole existence is driven by one singular, shared goal, achieving perfect atomic stability. To understand this quest, we need to know what happens when an atom tries to get stable. Basically, an ion is an electrically charged atom, or group of atoms, formed by the loss or gain of electrons. See, to get a full outer shell, just like a completely stable noble gas, atoms will actually shed or steal electrons. And when they pull off this little heist, they transform from neutral atoms into electrically charged particles called ions. It turns out the atomic world is basically divided into two distinct trading profiles. On one side, you've got the metals. These guys are natural givers. They want to lose electrons to other atoms, and when they do, they become positively charged cations. On the exact opposite side, we have the nonmetals, who desperately want to take. They grab electrons from other atoms, becoming negatively charged anions. Honestly, it's the perfect setup for a microscopic trade agreement. Let's look at sodium to see how this giving process actually plays out. It has 11 protons and 11 electrons, so it starts out totally neutral. But it has one pesky electron floating way out there in its outermost shell. By losing it, the atom drops right down to a full, perfectly stable lower shell. And since it just tossed away a negative charge, mathematically it becomes a 1+ positive sodium ion. On the flip side, take a look at chlorine. It's sitting there with 17 protons and 17 electrons, but its outer shell has 7 electrons. I mean, it is agonizingly close to stability. It needs just one single electron to reach a full outer shell, which, of course, it readily accepts. Because it took on an extra negative charge, boom, it transforms into a 1- negative chloride ion. This constant need to trade brings us right to Section 2, making the ionic bond, and the true power of electrostatic attraction. The crucial thing here is that these atoms don't transform in isolation. They actually make direct one-to-one trades. The moment that single electron is transferred from the metal, our sodium, directly to the nonmetal, our chlorine, something incredible happens. Suddenly, we have a positive ion and a negative ion sitting right next to each other. And you know the rule. Opposites attract. A ridiculously powerful electrostatic force of attraction immediately pulls them together. That intense force, that is exactly what we call an ionic bond. So how do we actually document this? Section 3, dot and cross diagrams, and visualizing the trade. Being able to clearly draw and communicate these invisible interactions on paper is absolutely vital, especially if you're gearing up for exams. When you're making a dot and cross diagram, you follow a strict 3-step process to perfectly track which atom gave away an electron and which one caught it. Step 1. Just draw the outer electron shells, using dots for one atom's electrons and crosses for the other. Step 2. Enclose your brand new, highly stable ions in large square brackets. And Step 3. You absolutely must write the overall charge clearly in the top right corner. Let's try applying this to a slightly tougher example, magnesium oxide. Magnesium is a group 2 metal, which means it's giving away 2 outer electrons to oxygen, which desperately needs, you guessed it, 2. Notice how the dots and crosses clearly map out exactly where those electrons went. We've got our squared brackets in place, and the top right corners show a perfectly balanced compound, with a 2+ charge on the magnesium ion and a 2- charge on the oxygen ion. Now let's scale things way up in Section 4, the giant lattice structure. We've seen one metal and one nonmetal link up on paper. But what actually happens when billions of these microscopic trade agreements go down at the exact same time in the real world? Well, these ions don't just form cute little isolated pairs. These electrostatic forces are acting in all directions simultaneously. A positive sodium ion attracts negative chloride ions to its top, bottom, left, right, front, and back. This intense attraction locks the alternating positive and negative ions into a massive, highly ordered, repeating 3D grid. We call this whole setup a giant lattice structure. And that brings us perfectly to our final section, real-world ionic properties. This is where we finally solve our initial mystery by connecting that microscopic 3D lattice we just talked about to the physical world we interact with every single day. Think about it. Ionic compounds are almost always solid at room temperature, and they have incredibly high melting and boiling points. Why? Because those strong electrostatic forces are pulling in every single direction within that giant lattice. It takes an extraordinary amount of thermal energy to literally break those billions of bonds apart. And there's the answer to our mystery. That is exactly why your simple table salt requires so much heat to melt. We can even predict properties based on the microscopic math. If you compare sodium chloride with magnesium oxide, the rule is the greater the ionic charge, like those 2+ and 2- charges we saw in magnesium oxide, the stronger the electrostatic glue holding that lattice together. Because those forces are stronger, magnesium oxide requires significantly more energy to break apart, giving it a way higher melting point than plain old table salt, which is only relying on a 1+ and 1- charge. Finally, let's talk electricity. For an electrical current to flow, you absolutely need freely moving charged particles. As a solid, the giant lattice locks those charged ions firmly in fixed positions, making them pretty terrible electrical conductors. But if you melt or dissolve the compound, that rigid lattice breaks apart. Suddenly, those charged ions are freed up to move around, instantly turning the molten or dissolved substance into a fantastic electrical conductor. As we wrap up this explainer, I really want to leave you with this thought. We just saw how this simple urge for a full electron shell creates a giant 3D lattice, which in turn makes a tiny grain of salt incredibly hard to melt. So the next time you look at that completely ordinary grain of salt, remember the invisible, massive atomic grid holding it all together. And ask yourself, what other microscopic mysteries are hiding in plain sight, quietly dictating the macroscopic world around you right now? Thanks for joining me to explore this fascinating atomic trade agreement.